We're going to continue on here. Not very cooperative today, so hope for the best. So we're talking chapter 15, and obviously we're talking about solutions. We talked about solubility with solutions and the idea of like dissolves like. And basically, what that means, as we talked about, the importance of those intermolecular forces, hydrogen bonding, dipole, dipole, dispersion forces. So, as we saw sort of in that experiment, when we go to mix together two solutions or molecules, whether or not they're going to kind of mix okay and be soluble in each other really depends on those intermolecular forces. So if they're using the same type of intermolecular force that they use with themselves, with whatever you're trying to mix them with, they should be pretty soluble in each other. If they're using very different sort of intermolecular forces, we're going to find a situation where they're really not going to mix because, for example, one's trying to do hydrogen bonding, one's trying to do dispersion forces, which are very, very different types of intermolecular forces. And as we saw sort of in that experiment, if you're mixing two solutions, you will see some layering happening between the different solutions because they're not mixing. And if you're doing a solid in a liquid or a solution, the solid will not dissolve in that situation. Now, if they are using similar types of intermolecular forces, you will see them mix with each other. So again, if you mix two solutions together and they are soluble in each other, it'll all look like one layer. If you have a solid that dissolves in the solution, it will dissolve. So what that means is when we talk about things being soluble or even miscible, which again is what we use when we're kind of doing two solutions together, you're good to go, if you have something that's ionic and something that is polar, those guys should be able to really interact well with each other. Again, they're going to do something, as we talked a little bit about the other day, which is known as ion-dipole interaction. So because ions have charges and polar molecules have a positive side and negative side, they're able to interact really well with each other. So as we talked about, basically all intermolecular forces are pretty much a very simple interaction of the positive side of one molecule interacts with the negative side of another. So that's how all intermolecular forces work. So this works really well. Obviously, if you have something that is polar and something that is polar, they also are not going to have any issues sort of mixing together. They both will be using either maybe hydrogen bonding. They both may be using dipole-dipole interactions, so they're not going to have any issues coming together. The one sometimes people sort of forget about is nonpolar and nonpolar. And these guys also will be very soluble in each other, like I think we saw when we did hexane. Thank you. Hexane and heptane together, they're both nonpolar molecules. The solution all mixed together, it looked like one. They're both going to be using dispersion forces, which allows them again to interact the same way with the other sort of molecule as they do with themselves. So really, in terms of being insoluble, you only kind of have the one real crossover that is not a good combination, and that is if you take something that is polar and mix it with something that is nonpolar, they're going to have a very, very hard time to maintain their interaction. Again, the polar substance is going to want to use something like hydrogen bonding or dipole-dipole interaction. And once again, nonpolar only has the option of dispersion forces. So dispersion forces being those really weak interactions will not be able to maintain the interaction with the polar molecule over a long period of time. They will eventually separate out. We also talked about some concentration type units. There's percent m/m, which is mass percent. That is the mass of the solute divided by the mass of the solution times 100%. Remember, as we talked about, it is this bottom part that's important. You do want to make sure that you get both the solvent plus the solute when you're doing the calculation. and very common in sort of percent mass to mass problems, they will give you those numbers sort of separate from one another. So again, a very common error that people make is they just kind of go with the solvent because it seems like the bigger number, rather than really getting the mass of the solution. So you want to make sure that you get both of those. We also talked about some other percent sort of concentrations. There's percent mass to volume, which is the mass of the solute divided by the mass of the solution times 100%. And then there's percent volume to volume, which is the volume of the solute divided by the volume of solution times 100%. The most common unit of concentration we finished up talking about was molarity. And molarity is big M moles per liter. And remember, you can kind of think of molarity as a formula because very often you are asked to solve for any one of those three things if you kind of have the other two. So you can almost like the density equation, you can kind of rearrange it similar. So if you want liters, that's going to be moles divided by molarity. And if you want moles, which is a super common conversion, liters times molarity is what you want to use there. You definitely want to use liters when you're using molarity because that will give you moles, which is typically what you're looking for. You definitely don't want to use milliliters because you will not get moles, you will get millimoles. And most likely your answer will be off by like a factor of 1,000. So you want to make sure that you get the right one. Now, if you do have the molarity given to you, like 4.50 molar sodium chloride. Remember that it's a very good idea to maybe kind of take a more conversion factor approach and definitely get rid of the big M in your calculation. And that would be that you had 4.5 moles per liter. The number always stays with the moles part and is always per 1 liter. And you could use it as a conversion factor. You could definitely flip it around and put the liters up on top. And you could go with the 4.50 in this case, moles. The reason for that is, again, cannot tell you how many times I've seen people do calculations where they just leave the big M and they have no clue about the volume part of it, where it's at, or if there's even volume. Most of the time, they will just think it is moles when they see the big M. So you want to make sure you maybe convert it into both those units so that you can see both of them. It is. Thank you very much. It is supposed to be that. I don't think this is going to let me erase it, so I'm just going to scratch it out using a different version here that everyone do on work. So thank you. It is volume of solution on that one. Yes. And on those percentages, they typically will give you kind of the volume of the solution in most cases. So you don't have to worry about kind of the separation of solute and solvent. Any questions on any of that there? It's supposed to be solute over solution. Solute. Yeah. Yeah. Other questions? All right. So I think I move it this way. Go try that. Let's see if it'll work. All right. The next thing we're going to talk about is dilutions. And dilutions is the process where we take a solution that is more concentrated and we dilute it down to a more dilute concentration. Typically, when we do a dilution, the only thing that we change is the amount of solvent that we add. So, a lot of cases, that's water. Not always water, but most cases, it's water. And when we add more solvent, what ends up happening is we end up with a lower concentration of that solution than we started with. Now, the one thing that doesn't change is actually how much solute you have in that solution. The moles of the solute, which is really, by the way, when you look at a solution, the solute is the stuff that's reacting. So you have a 4.5 molar sodium chloride solution. That 4.5 moles per liter of sodium chloride is what's really doing the reaction. So the moles of the solute before and after dilution stays the same. That is why the molarity goes down, because if you think about the actual molarity sort of formula, is moles of solute over liters of solution. And once again, the solution is both the solute plus the solvent. So when you add more water and you do a dilution, you're actually adding more solvent, and the only thing that gets bigger is the bottom number here. And because this bottom number gets bigger, the molarity goes down because the solution part gets bigger, so the molarity drops down. Again, if you have some ice and it melts in your drink, obviously it tastes a lot more dilute than it did when you originally got it. Again, because of the addition of all that extra water molecules that are now floating around in the solution. There is actually a formula for dilution, and this is one way that you can make a dilution. Again, you can take a little bit of water in a volumetric flask. You could add some of your more concentrated solution to it, top it off there to the line as we talked about when we were talking about making that solution. And if you mix it up really well, you'll now have a more dilute solution because of the addition of the water. To do our calculation, I would say most people roll with this formula here, which is M1 V1 equals M2 V2. This is typically before the dilution, and this is typically after. It doesn't really matter, but that's just typically how people usually arrange it, to be honest with you. And you could use this formula to figure out, if you added some water to a solution, what the new molarity would be. If you wanted to create a solution with a specific molarity, how much water maybe you need, and how much of the more concentrated solution you would need. So a more generic one that people kind of put in books these days is C1V1 equals C2V2. And do that way, so don't do that. In this case, the C is just generic for concentration. So technically speaking, you could put any concentration unit you want in there. You could use molarity, you could use actually percent mass to mass, you could use whatever you want, as long as they are both on the same side. So I would say most people kind of roll with this formula because the M1 V1 equals M2 V2, because again, molarity is probably in 9 times out of 10, maybe even more. That's probably the unit of concentration you're going to use. And so most people kind of roll with that formula right there, the M1 V1 equals M2 V2. If you solve typically for M1, that is the concentration of the more concentrated solution. If you solve for V1, that is how much of the more concentrated solution you need to make your dilute solution. M2 is the concentration of the more dilute solution, and V2 is the volume of the dilute solution that you're going to make. Let's take a look at one here. All right, what volume of 19 molar sodium hydroxide must be used to make 1 liter of a 0.15 molar sodium hydroxide? Just doing a dilution. We're starting with a 19 molar sodium hydroxide solution. We eventually want to make something that is 0.15 molar. That concentration is much, much less than what we started with. So this is definitely a M1 V1 equals M2. Come on. M2 V2 situation here. And here, what we basically got going on is we got a bottle sitting here. If it lets me draw my bottle. There you go. 19 molar sodium hydroxide. And we basically want to make a new bottle or beaker that has a total volume here of 1 liter, which is 1,000 milliliters, right? And we can have the molarity there of 0.15. And obviously here, this would be our M1. This would be our 2s, what we're trying to make. So clearly here, we do not know what V1 is. So that is what we want to kind of do. By the way, in this particular formula, and if you are specifically using this formula, Your volume does not need to be in liters. It can be in milliliters on both sides, and everything will cancel out okay. If you want to, you could convert it into liters on both sides, it's fine. But you could actually leave it in milliliters if you want to use this formula. Now, if you are not using this formula and you're just using molarity by itself, and you're not doing this formula or a dilution problem, you 100% of the time need to convert to liters to make sure everything gets in the right units. But in this particular formula, because there's volume on both sides, you can put them both in milliliters and everything will actually cancel out correctly in this case. In this case here, we're going to solve for V1. So V1 in this case will be M2, V2, M1. We're going to put it in here. That's going to get us here for M2 0.15 molar. I'll go right now with the liters. And again, I could have done 1,000 milliliters if I wanted to. And our original molarity, which is our M1, is 19. Once again, when we do that, this molarity is going to cancel. And because I went in with liters here, my answer is going to be in liters when it comes out. If you went in with milliliters, your answer would be in milliliters if you came out at this point. 0.15 divided by 19. That's going to get me here 0.0079 liters, or approximately 7.9 milliliters. First off, any questions on the calculation? What does that number really mean? That number really means that is how much you would go into the more concentrated bottle and take out. So you would move over, I'll do the milliliters, just a little easier numbers, not so many zeros. You would move over 7.9 milliliters of your more concentrated solution in this case. Now, we do want a total of 1,000 milliliters or 1 liter when it's all said and done. Do I put in there 1,000 milliliters of water in this case with it? I do not, because if I did, again, I would be at 1,000 and it's like 7.9 milliliters, which is too much. So a very common question is sometimes asked when you're doing dilutions is how much water you need to add or how much solvent you need to add. And typically the volume of the water is V2 minus V1. And in this particular case, if we take 1,000 minus 7.9 milliliters, again, looking at it in terms of milliliters, we would need to put in there with our 7.9 milliliters about 992.1 milliliters of water with it. So we would then put in there 992.1 milliliters of water. That gives us our total volume of 1 liter. And once we mix that all together, we then should have a solution that has a molarity of 0.15 molar. Any questions on that one there? Okay. All right, so let's take a look at another one here. What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar solution of calcium nitrate? We got a calcium nitrate solution we're trying to make that is a lower concentration than the original calcium nitrate solution. So once again, very much like the last one, we got kind of a bottle there of 5 molar calcium nitrate. And that would be like our M1. We once again want to make kind of a new bottle there, our container that is a volume of 500 milliliters and a new molarity of 0.25 molar in this case. Once again, that is going to be our M1 V1 equals M2 V2, or your C1 V1 equals C2 V2, your choice. Here again, we do not have V1, so we're going to solve for V1 by dividing the M1 to the other side. That is going to get us here. Come on. There we go. That is a 1. And we'll put our numbers in. We got 0.25 molar. As I mentioned a second ago, you can leave this in milliliters here. If you want to convert to liters, that's perfectly fine as well. Again, your answer will just be in liters versus this answer will be in milliliters. So it's your call. And again, we'll divide by our M1, which is 5 molar. And this is why, again, you can't leave it in milliliters because at this point the molarities will cancel and that will leave you basically milliliters left over, and that's going to be the units. And that should get you something like 25 milliliters. Again, in this case, though, you do want to make sure you read these questions carefully, especially dilution questions, because very much like this one, they oftentimes will ask how you make the solution, how much water you need to add, and that is the question here. So once again, that 25 is how much we would take out of the original container. And now we want to find the volume of water, which is really what it was asking. So we'll take our V2, which is our total volume at the end, minus our V1, which is 25 we just calculated there. That's going to give us 475 milliliters of water. Needs to be added here. So again, we would add something like 475. That again is going to give us a total volume of 500 milliliters when we mix it together. And at that point, once you do, you again should have a solution sitting there that is 0.25 molar. Any questions on dilutions there? All right, so the next thing we're going to talk about is stoichiometry involving solutions. And up to this point, we have done stoichiometry involving a number of things, just basic stoichiometry, grams to moles. We also talked about stoichiometry in the gas chapter where we do gas stoichiometry. So no different here. We can do stoichiometry to involve solutions. It is still your same basic steps in your stoichiometry process there. You want to balance your equation. You want to change whatever they give you to moles. You want to determine if it is a limiting reagent problem, and if so, you need to do a calculation to determine which one's the limiting reagent. You want to calculate the mole to mole required. So you want to do your mole to mole relationship, and then finally your moles to some other unit. Now, the main difference when you're doing sort of solution stoichiometry a lot of times is right around here. We oftentimes can use molarity and volume to get the moles. So since molarity is moles per liter, the moles is liters times molarity. And once again here, you definitely want to make sure you are in liters on this calculation so you're not off. That is what you want to make sure of. The other place that sometimes is different is at the end. So a lot of times, as we've done previously, maybe at the end we have moles and we use molar mass to figure out how many grams we would produce. Sometimes, a lot of times, we're interested in maybe the molarity at the end of the solution, or maybe we're interested in the volume. So at the end, once again, using molarity sort of formula, we sometimes will solve for the volume, which is moles divided by molarity. Or really, in some cases, we will actually just solve for molarity. So those are kind of two endings that are very common in solution stoichiometry. Everything else in between is exactly the same. And you can have a mixture of different types of stoichiometry together. For example, you may start out the problem with grams to moles and then end up using molarity at the end. You may use molarity at the beginning and then at the end figure out maybe grams, or you may just use molarity on both spots as well. So again, you can combo these things together. And again, things do work kind of the same way. Any questions on that there? Let's take a look at one. We're just going to do, I think, just the first part here. So we'll get rid of this part, I think. All right, so let's just say that we wanted to calculate the mass of solid sodium sulfate that must be added to 250 milliliters of a 0.2 molar solution of barium nitrate to basically make the precipitate barium sulfate. So like normal in this case, we are not given We are not given the formula, so we got to start with the formula. So sodium sulfate is Na2SO4, and we need to add that to barium nitrate, BaNO3 2. These are both aqueous because of solubility rules we've talked about in previous chapters. That also should look familiar to you because this is a double displacement reaction, which means on the product side, we're going to switch partners. So the sodium will hook up with the nitrate and make NaNO3. Remember here it makes NaNO3. It does not make Na2NO3. That is not a proper formula. So you want to put everything together properly. Sodium +1, nitrate -1. So one of each of them when they come together. Barium is +2 and sulfate is -2, which means when you put those guys together, you end up with this, and that's going to be your solid, and that is your aqueous in this case. First off, any questions on that? Obviously, that is the proper formulas for everything. As we talked about before, what you want to do is make sure you get the proper formulas down first, and then you should balance it. So obviously this is not balanced, so I believe we need a 2 right about there. And I think that's actually going to do it in terms of balancing. So now we could think about what we're doing in this problem, and obviously here we want to know the mass of sodium sulfate. So we want to know the mass of the sodium sulfate, and we are starting with 250 milliliters, 0.2 molar barium nitrate. So this is pretty much all the information that is given to us. So remember that whenever you do a stoichiometry problem, the thing that you want to first figure out is it a limiting reagent problem? And the way you determine it's a limiting reagent problem, as we've talked about, is are you given enough information to figure out the moles of each reactant? And in this particular case, since we are trying to find the grams of a reactant, we obviously is not a limiting reagent problem. We only can get the moles. This is the only thing that we can get moles from. So this is really just a basic stoichiometry problem. So we're just going to follow our 4 steps without the limiting reagent calculation here. So first step, balanced equation is done. Second step is convert whatever they give us to moles. And in this case, we are given the volume and the molarity. So we're actually going to use that to get our moles rather than grams to moles. So this is a major difference in terms of solution stoichiometry, how you get the moles rather than going to the periodic table and get the molar mass. You have the volume, you have the molarity. You can get the moles from that, as obviously molarity is moles per liter. So once again, you got this guy and you got this guy. You could solve for this. We do need to, again here, convert our volume into liters so everything cancels out correctly. So this is, again, a common conversion in these type of problems, 250 milliliters. There's 1,000 milliliters in a liter. That gives us 0.25 liters. Now that we have that, we could take our 0.25 liters. We could times it by the molarity, as obviously here our moles will equal liters times molarity. As I mentioned before, I will not do a calculation where I keep the big M. I'm going to use it as a conversion factor. So that 0.2 molar again means 0.2 moles per liter. Or you could flip it around, do a liter on top and 0.2 moles on the bottom. Once again here, dimensional analysis, it's just opposites cancel. So we do need our molarity in this fashion, where liters are on the bottom. So 0.2 moles per liter. Again, when we multiply the top and divide the bottom like normal dimensional analysis, our liters are going to cancel. And that's going to give us our moles here of our barium nitrate, which will be 0.25 times zero point 0.2. Looks like 0.05 moles of barium nitrate. So again, one of the differences in these type problems is how we get the moles at the beginning. And sometimes you may still do grams to moles as well. So sometimes you may still kind of do the grams to moles part. At this point, we are not interested in barium nitrate. We are interested in the sodium sulfate. So that brings us to our third step, which is our mole to mole relationship from the equation. And from the equation, we can see that for every 1 mole of sodium sulfate, we get 1 mole of barium nitrate. So we're going to use that in our third step, which again really is the stoichiometry part. So we're going to go 0.05, which was our answer from the previous step, of barium nitrate. Remember, again, opposites cancel, so we need, I'll just do it this way then. We need barium nitrate on the bottom there. So that is going to be 1 mole of barium nitrate on the bottom, gives us 1 mole of sodium sulfate up on top. The moles of barium nitrate will cancel, and we'll end up now with 0.05 moles of sodium sulfate at this point. Once again, if by some chance we were just looking for moles, we would be done with the calculation. But here we're actually looking for grams. So the last step here is a normal sort of stoichiometry step. We're going to take moles into grams. That means we do need to visit the periodic table and get the molar mass of Na2SO4. And if you do that, that is 2 sodiums at 22.99 each, plus a 3207 for the sulfur, plus 4 times 16 for the oxygens. So from the periodic table, getting the molar mass, 142.1 grams per mole. That obviously is going to be our conversion factor here to finish out the calculation. So we'll go 0.05 moles of sodium sulfate. And we can see here we want grams up on top, 142.1 grams per mole of sodium sulfate. And that's going to tell us here we got about 7.1 grams of sodium sulfate is needed in this case. Any questions on that there? So hopefully you can see it really is the same 4 steps here in our stoichiometry process. Difference is, again, either step 2 or 4. Somewhere along the way there, you're going to use molarity and involved in either getting moles or volume or actually calculating the molarity along the way. Any questions on that there? Yeah. All right, so let's take a look at this one here and see another sort of example. We want to calculate the mass of calcium carbonate that forms when we mix calcium nitrate with sodium carbonate. So once again, it is a stoichiometry problem, so we'll start with our equation. So obviously here we are starting with calcium nitrate plus some sodium carbonate. And once again, it is a double displacement, so the calcium will end up with the carbonate. Calcium plus 2, carbonate minus 2 gives us a CaCO3. That is our solid. And the sodium will hook up with the nitrate, which once again will be plus 1 and minus 1 coming together, giving us our proper formula that looks something like that. And again, we do need to balance it. So once again here, I think a 2 is what was needed in this case to balance it. In this particular case, we are looking for how many grams of our calcium carbonate. And we are given that we're starting with 25 milliliters of a 0.1 molar solution of calcium nitrate and 20 milliliters of a 0.15 molar sodium carbonate solution. So once again, we do have a stoichiometry problem, which means we do want to make sure that it's a limiting reagent problem or not a limiting reagent problem. And in this case, because we have the molarity and the volume, that is going to allow us to get to moles of that guy pretty easily. And we also have the molarity and volume here, which means we could also get to moles of that guy. So once again, that is the tell sign that it is a limiting reagent problem if you could get the moles of each reactant once you start the problem. So again, somewhere along the way there, we need to kind of think about the limiting reagent and figure that out. So the beginning part's still the same. We're going to convert everybody into moles. So our moles of calcium nitrate in this case is going to be the volume, which once again, we do need to convert into liters. So divide 25 by 1,000 and you'll get 0.025 liters. We're going to multiply that by the molarity. And again, we're going to get rid of the big M here, and that means it is 0.1 moles per liter. And again, that is what the big M stands for. When we multiply here, the liters will cancel, and that's going to get us 0.025 times 0.1, 0.0025 moles of calcium nitrate. We're going to do the exact same thing for our other reactant here. So converting our volume into liters, we can figure out our moles of sodium carbonate. So dividing the 20 by 1,000 gives us 0.02 liters, timesing it by the molarity, and that is 0.15. So 0.150 moles per liter. Once again, that is what the big M stands for. And again, multiplying here, our liters will cancel, and we'll end up with 0.02 times 0.15, 0.003 moles of sodium carbonate. Any questions on that there? So again, just slightly different than grams to moles using the molar mass. Molarity, volume gets us to moles here. Once again, because this is a limiting reagent problem, we could think of this as our starting amount for each of these. So remember, one way to figure out which one's the limiting reagent is to figure out how much of the other reactant you need to use up the first one. So here I'm going to figure out how much sodium carbonate is needed. So to do that, I'll take the moles of my calcium nitrate, 0.0025 that I'm starting with. I'm going to now do the mole-to-mole relationship between the two reactants, which from the equation is a 1-to-1 relationship. So we're going to go opposites here to cancel. 1 mole of calcium nitrate from the balanced equation coefficient gives me 1 mole of sodium carbonate here. That's going to basically keep me the same number, 0.0025 moles of sodium carbonate is needed. Remember that what we want to do at this point is compare that number that's needed to how much we're starting with. And in this case, we're starting with 0.003, and we only need 0.0025. So we have enough And because of that, that means the sodium carbonate's our excess reagent, and the calcium nitrate is our limiting reagent in this case. Any questions on that there? So again, you can see even in a solution stoichiometry, you still got to kind of think about limiting reagents and make sure it's not a limiting reagent problem. At this point, we can continue on with our normal stoichiometry steps using our limiting reagent starting amount, which is 0.0025 moles of calcium nitrate. Once again, we can now go to the equation and find the relationship between the calcium nitrate, which is our limiting reagent, and our product, which is the calcium carbonate. And we've got a couple of lucky ones so far. They're all been 1-to-1. Obviously, as you may know, it's not going to always be that way, but 1 mole of calcium carbonate from the equation gives me 1 mole of calcium nitrate. That obviously is going to get me 0.0025 moles of calcium carbonate. By the way, that again would be our theoretical yield in moles, but here we are looking for grams. So the last step here is the molar mass from the periodic table of calcium carbonate. So again, if you go to the periodic table, you got a 4008 for your calcium, you got a 1201 for your carbon, and you got 3 times 16 for your oxygen, 100.1 grams per mole from the periodic table is the molar mass, and our conversion factor to finish out the problem here, 0.0025 moles of calcium carbonate. I guess we'll just do it that way there. And we're going to put the grams up on top and the moles on the bottom. And that's going to get us here, looks like 0.25 grams of calcium carbonate would be formed. That also is the theoretical yield in grams in this case. Any question on those steps? So hopefully you're seeing it is the same steps that we've done previously. Just again, how we get maybe moles is different, and maybe at the end of the calculation as well can be different using molarity. But everything kind of in the middle of the sandwich there is going to still be the same steps. Any questions on that there? Okay. So this is one type of sort of solution stoichiometry, kind of similar to a precipitation experiment we did where we made the yellow. Another place where we definitely see solution stoichiometry involved is what we're going to do in lab today, which is titrations. And titrations is a process where to figure out what we're trying to figure out in that process, we definitely use solution stoichiometry to do so. Let's see here. Now, we're going to talk about an acid and base reaction. And most of the time when you do a titration, and not all titrations will involve acid and bases, but most commonly they do. When we do an acid-base reaction, we will get a neutralization reaction that we talked about before. So for example, if we took hydrochloric acid plus some sodium hydroxide, we will get a salt and water like we talked about when we talked about types of reactions. So we will get water formed here, and we will get NaCl, which is a salt. So again, we form water plus a salt in a reaction of an acid and a base in this case. Now, if you went through the whole total ionic equation, net ionic equation, for any combination of strong acid, strong base, you would, for example, break apart the hydrochloric acid because it's a strong electrolyte. You would break apart the sodium hydroxide because it's a strong electrolyte as well. You will keep together the water because it's a liquid. And you would break apart your sodium chloride because it is a strong electrolyte as well. You would find your spectator ions, which is the chloride on both sides and the sodium on both sides. And you get basically the net ionic equation that's happening here when you take an acid and a base together. The H plus from the acid will hook up with the OH minus from the base and basically make water, which again is why it's referred to as a neutralization reaction in this particular case. Now, one of the processes that we use when we do these type of problems is the process known as titration. And in a process of titration, you usually have two types of solutions. You have usually one solution that's a known solution. And what that means is you know pretty much everything about it. You know typically the molarity of it, and you usually know the volume that you used of it. And that's really good for molarity as well, which again is moles per liter. So usually in your known solution, you kind of have both of those things given to you. Now, you typically will have an unknown solution. And the unknown solution is a solution you do not know everything about. I would say most commonly, you oftentimes may not know the molarity of it. You may not know how many moles of it you're starting with. That's very, very common. Now, in the process of a titration, we use a burette, which is very similar to that tube we used when we did the gas experiment, that kind of long tube. So we usually use this burette. And it is much like that tube, the volume increases as it goes down. So we fill it from the top, it increases. So once again, if you found yourself with a volume right about there, this is actually 2.5 milliliters and not 3. So you want to make sure you always read it correctly. Now, we usually will have a beaker, a flask, something down here. So for example, you could put your acid down here and you could put your base up here. You could also do it the other way around. You could put your acid in the bottom, your base in the bottom, and you could add acid to it. So it just depends. But most commonly for you guys, this is probably the titration you most commonly will do. You commonly in an acid-base situation, put the base up on the burette and down in the bottom there is going to be the acid. But again, it can be the other way around. So very commonly what happens is we will start adding, and let's just say that the base is our known solution. And let's just say the acid is our unknown solution. And what typically happens is we will slowly add, like our sodium hydroxide, for example, to our HCl if we were doing like that titration. And we will slowly add it until we reach what is known as the equivalence point. And the equivalence point in an acid-base titration is oftentimes thought of as when the reaction is over. And that is the point where the moles of the acid will equal the moles of the base. So that is the point, kind of like you used up everything, the reaction is done at that point. Now, how do you know when to stop? We typically will use an indicator. And an indicator is actually a weak acid usually. And it will change color near your equivalence point. So it will actually have a color change near your equivalence point. For example, they actually work over a pH range, say like the one we're going to use today, which is phenolphthalein. This lets me write it, phenolphthalein. Come on, there we go. Phenolphthalein. It works on a pH range of 8.3 to 10. It actually works in the basic range. Phenolphthalein is colorless in acidic solution, is colorless in neutral solution, but turns a lovely shade of pink in a basic solution around 8.3. Actually, at 8.3, it's colorless. And as it heads down to 10, it gets pinker. So 8.3 colorless and super light pink, dark, 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 super dark pink as you head all the way down and your pH changes in your titration. Now, when you see that change color, you want to kind of stop your titration. Typically, you want to stop your titration once you see the lightest, if you're using phenolphthalein, for example, You want to stop it when you see the lightest color of pink that you can see. So light pink that you oftentimes have to put like a white piece of paper underneath it to kind of see the pink. And that's ideally where you want to stop. What you will probably encounter, which is very common as well, is you'll get kind of a dark pink, and it can change really quickly. You could have a solution that has no color and you add one drop, and now you got like a super dark pink, and it can change really quickly. And it changes really quickly because as you get near the equivalence point, what happens is the pH changes a lot, but the volume doesn't. So you literally could add one drop in, and before that you had no color, and then it could shoot to dark pink just from that one drop because the pH changes a lot. The indicator color is going to change a lot, even though you just added like one drop. It's not going to make that big of a difference. So we continuously do this. Now, when we do a titration, there's two things that we always want to record, which is we want to record the initial volume that we're starting with in our burette, and we want to record the final volume once we're done with the titration. And you could get the volume of base, for example, added by taking the final volume minus the initial volume. And that's a really important number. So when you're done with the titration, you will know, for example, the volume of the base you use. You also know its molarity. So you'll know the volume you use and the molarity. You then will be able to figure out the moles, for example, of your known solution. In this case, maybe the base. You then can use stoichiometry to figure out how many moles of base to moles of acid that would be. And now you'll have the moles of the acid. And that means for this unknown solution, maybe you want to know the molarity, and you know the volume of acid you started with. You can use stoichiometry to figure out the moles of the acid based on how much sodium hydroxide, and that will allow you to calculate something like molarity, which is a very common ending to this type of process. These are really just solution stoichiometry problems that occur. So let's take a look at one here and sort of see. Now, let's say we're doing a titration, which is sometimes just referred to as a neutralization reaction. We want to know what volume of 0.15 molar nitric acid is needed to neutralize 45 milliliters of 0.55 molar KOH. Now, in this particular case, if we drew sort of a picture of like a titration that you could do to do this, you would have maybe in this case the KOH, which is the potassium hydroxide on the bottom, and you know everything about this. You know the molarity of it is 0.55 molar. You know the volume you're starting with, which is 45 milliliters. Now, if you put up in your burette your nitric acid, the only thing you know of it is its molarity, which is 0.15 molar. So remember that molarity is moles per liter. So we do know the molarity of the nitric acid. We are looking for the volume. So what we're going to do is use stoichiometry to figure out the moles so that we can then figure out the volume. So really what this is just a fancy solution stoichiometry problem wrapped up in what they call a titration problem. So it's really just solution stoichiometry. So what that means is step number one of any stoichiometry is I need an equation. So that's going to be my nitric acid plus my base. And this is also a double displacement reaction where we're going to switch partners. And we're going to make water always in this reaction, and our salt, which in this case is potassium, which is +1, and nitrate, which is -1, and we'll end up with potassium nitrate in this case. And this would be our step number one balanced equation. We do want to make sure it is balanced, so if you look on both sides, we got a couple of hydrogens, one nitrate, and one oxygen, 4 oxygens, so we're good. Next thing we want to think about is just like what type of stoichiometry problem is this? Well, we have the molarity of this guy. We are looking for the volume. We have the molarity of the KOH, which was given to us, 0.55 molar, and we have 45 milliliters of it. So the first good news is this is just a basic stoichiometry problem because we cannot get moles of both reactants. So it's just a basic problem. At this point, we can then convert to moles using the only information that will allow us to do that, which is the KOH. So step number 2, we're going to take our volume of KOH, which is 45 milliliters. Once again, we do need to divide it by 1,000 to convert it into liters. We're going to use our molarity where we can see both units. So that is 0.55 moles per liter of KOH. That is going to give us our moles of KOH. So 0.045 times 0.55. 0.02475. I'm not going to round right now. I'll kind of keep it. Remember that ultimately we need the moles of nitric acid. So that is where the stoichiometry comes into play. So mole to mole relationship time. It is a 1 mole of KOH to a 1 mole of nitric acid. That is the stoichiometry part of it. So we'll take our number from the previous step. And we'll do our mole to mole relationship. And now we have 0.02475 moles of nitric acid. So here again, we're using stoichiometry to figure out how many moles of nitric acid was needed in this reaction by using our known solution that we know everything about. And that allows us to figure out something about our unknown solution. At this point, we don't want moles, but we do want volume. So now that we have the moles needed, which is our 0.02475, we can now use our molarity formula here at the end for the last step to figure out the volume. So using our molarity formula and solving for volume, liters to moles divided by molarity, we can use our information here. We'll take our 0.02475 moles of nitric acid. We will use our molarity of the nitric acid, which we knew, which was 0.15 moles per liter of nitric acid. The moles are going to cancel. And we're going to divide it by 0.15. That's going to give us 0.165 liters of nitric acid. Liters of nitric acid. And again, we can convert that by multiplying by 1,000. That is 165 milliliters of nitric acid is necessary. So if we were doing this titration, we would have to add 165 milliliters to our beaker to reach the equivalence point and see our color change in our indicator and our solution kind of change. Any questions on that there? Yeah, it's the bottom that's going to cut up there is 0.15 moles per liter of nitric acid. Yep. Other questions on that? All right, let's try one more here. So why don't you give this a try? What volume of 0.355 molar sodium hydroxide is required to react with 125 milliliters of 0.5 molar sulfuric acid? Okay, so since we're getting to the end, we'll finish this next time, and we're going to do some calculation anyways in lab that's similar to these. Just a reminder, though, of something that's very common mistake that people make when they do these type of problems, especially titration problems, is a lot of people want to use the M1V1 equals M2V2 formula that we saw with dilutions. And you may even see people online and stuff like that say that that is a titration formula. And it will work, but only for a specific type of relationship, a one-to-one relationship. If it is not a one-to-one relationship in your balanced equation, you will get the wrong answers. So you should always show these type of problems using stoichiometry, dimensional analysis. You should not, and you will not get full credit if you use M1 V1 equals M2 V2 on these type of problems. And again, just be careful because it will not work, give you the right answer always, depending on your equation and stuff like that. All right, we'll see everybody.